Okay, so you have gamma, r at the top, tt, tt's at the bottom. What is that? It takes gtt, which is the coefficient of the t square, takes the derivative of it with respect to the r coordinate, and then divides it by twice the metric coefficient of the r. Gamma is gtt prime over minus 2 grr. In other words, you have the dt square and the dr square. It takes the coefficient in front of the dt square, takes a derivative with respect to this coordinate, the r coordinate, and divides that by this metric coefficient. So the question becomes, is there such a construct in Newtonian gravity which would lead us to suspect that in this higher level theory we have something like this? And if one would in fact have such a theory, which of course one does, we would then expect what? We'll expect to see the following. We have a space-time metric, and remember again, this is, I put no special relativity in it, okay? ds square, we had this function gtt dt square plus the spatial part. What is this function gtt going to be? Well, we know that gtt prime is a, so what is gtt? We have gtt, we have a is equal to a equals phi prime, which corresponded to gamma. This is gamma prime equals phi prime, and right. And we know that in differential geometry, this is that. So we can now relate these two things. In gravity theory, the acceleration is phi prime, which means that the world line curvature is phi prime, which means that we expect that in our higher level theory, the connection will be phi prime. But we know that the connection should be the derivative of a metric coefficient. So that means that our connection is the derivative of phi prime, derivative of phi, which means our metric is, we have gtt prime equals phi prime. It's the same thing. Okay, again, the connection in this curved space-time theory, according to differential geometry, would be the derivative of the potential of the metric coefficient, in this case the time warping metric coefficient. And we know from gravity theory that that which corresponds to this connection is the acceleration, and that is in fact the derivative of phi prime. So phi prime is the candidate to be equal to gt prime. If that's the case, then gtt is simply a constant plus some other constant times phi. Alright, these two derivatives are the same, and this is simply that. Okay, let me just write it bigger here. gtt prime to phi prime, so gtt is equal to alpha plus beta phi. Okay? Which means that we're going to stick it in here. So we have ds squared, the metric of space-time, is equal to alpha plus beta phi, where phi is the gravitational potential, times dt squared plus the spatial phi. Where there's no function, this is totally flat in our theory. Because we only have time warping. All we need is time warping to take into account the curvature of the world line, which is the acceleration. Now, this, of course, our intuition tells us that in the absence of any field, this should be 1. Correct? So we're going to have a 1 over here, and when this potential vanishes, it just becomes dt squared. So we expect this. So we've come all this way without special relativity. We've, in an intuitive way, we haven't derived, of course you can't exactly derive these things, and it's all post-hoc. People only thought of any of this only after Einstein came up with general relativity, and only years later when they went down in depth and understood it well enough to see that a lot of this is in Newtonian gravity. Most of the stuff that I did here is not standard, right? Some of it comes up from my own thinking and ways of presenting and so on. Some of it is standard. And it's really, really nice how one sees that one can motivate the idea that space-time is curved, there's a connection, there's a Riemann tensor, and underneath it all is a metric, and that in the case of Newtonian gravity, you end up with this. Since we don't have time, I won't go much further. I'll just do in 1 minute, I'll just show you like a hint of how you would find what this what this should be in a different way. Most of the stuff that I did here is not standard, right? Some of it comes up from my own thinking and ways of presenting and so on. Some of it is standard. And it's really, really nice how one sees that one can motivate the idea that space-time is curved, there's a connection, there's a real tensor, and underneath it all is a metric, and that in the case of Newtonian gravity, you end up with this. To show you like a hint of how you would find what this should be in a different way. And in fact, you can do this in your head as a like by inspection really. If I did t goes to t to the 2/3, this is my transformation. What is dt d prime be? 2/3 t to the minus, right? All right, dt is 2/3 t to the minus 1/3, right? What would dt prime square be? Square that and get to the minus 2/3, which means 1 over what it was before, which is 1 over r, right? So dt prime square will be proportional to 1 over r. And that tells you that the factor is the potential, 1 over r. ds squared is equal to c dt squared plus the spatial part. I'm just going to have some function in here, which is the potential. Keep c the way it is, and like that, which is what we do. That's this. See clearly here that the amount of time passing will be different depending on the potential, but you can also see it from here, and you can see the amount is like t to the 2/3. In other words, you're going to have a factor of 1 over r relative to the previous one. There's a time stretching, which if you do dt and dt squared, which you have over here, you need a factor of 1 over r. If you do all these constant factors, you're going to get exactly gm over r. And obviously this constant has to be 1. So taking Newtonian gravity very seriously, taking the equivalence principle very seriously, just looking at this radial infall, t to the 2/3, if you say no, it's not t to the 2/3, it's got to be alpha t, because it's a straight world line because it's inertial, right away tells you time is stretched, and tells you that the factor is the potential, 1 over r. So you can kind of collapse this whole hour and whatever into those few seconds and say, okay, immediately I can see from the equivalence principle that I'm going to have a space-time metric and my time is warped and I'm going to have 1 plus something over r. And that's, of course, the Schwarzschild solution, except for the fact that we don't have spatial curvature. Einstein's original theory, or one of the theories that he was working with before 1915, at 1913 he came up with what's now called the Entwurf paper, the Entwurf metric, and this is exactly the metric that he presented, with a flat space over here. And as a result of not having the spatial curvature, he came up with the wrong prediction for the bending of light. And had the expedition gone out earlier, they would have found that his theory was incorrect. When he finally added in spatial curvature in here, he ended up with the right amount of curvature. But this was, in fact, what he originally proposed. However, he didn't propose it for the reasons that I'm saying. He proposed it for very different reasons. The equivalence principle with this LN, the equivalence principle shows that light will bend. You know, the elevator falling, if you shoot light from one side of the elevator to the other, and it's accelerating down, by the time it goes down, by the time the light has hit the other side, the elevator is over here. So the detector is now further down, so the light has seemingly bent. So you can come up with arguments showing that light is bent in gravity. If light is bent, when does light bend in light theory? When there's a diffraction, when there's a refraction coefficient, right? Which basically you can think of as the speed of light changing. Speed of light changes in a medium. And he came from special relativity, which we didn't use. In special relativity, you have ds squared is equal to c dt squared plus the spatial part. So he said the speed of light should vary, and that will give you refraction, and that will explain what happens in gravity. So you had c as a function of r dt squared. And only later did he say, you know what, I want to keep the speed of light constant. Instead of having the speed of light changing, I'm just going to have some other function in here, which is the potential. Keep c the way it is, and like that, which is what we did. So we came up with the same arguments, but without using special relativity. Okay, thank you very much. I know the time is a little long. If we want to make a metric, we're going to square it and add it to the other things, right? We're going to have just flat free space, just ordinary. We had no reason to make this anything over here. This was just to give us context. But here we're going to have some function of r. Now this has to reduce to 1 in the end, right? If there's no gravitational field, if there's no mass, we want this to be 1, not 0. So it'll be something like that. Of course, we know that there's supposed to be a signature thing here that's a little bit more complicated. We may or may not be able to find that out with special relativity. It's possible that we maybe, by the fact that gravity is attractive, maybe that would give us a hint and so on.